Here we're going to start chapter 18 and talk about columns. A column is a member subjected to an axial compressive load whose length dimension is significantly larger than the cross-section dimension. It's also known as a compression member, and examples of columns are pillars, pedestals, props, masts, and piers. There are generally three categories of common columns based on their failure mode: short, intermediate, and then long. So short columns, that's what we've been talking about all along. You got normal compressive stresses, sigma equals P over A, as discussed in previous lessons. They will fail by yielding if the column is made from a ductile material. If the column is made from a brittle material, it will crush. But if you have a long column, also known as a slender column, it will fail by elastic buckling that are at stress levels below the elastic range. So it's actually going to fail at lower stress levels than we would predict using material failure or yield strength or stuff like that. So buckling. Buckling is best defined as a bending action that is a result of a compressive load. Now, intermediate columns are somewhere between the two extremes. Most columns are intermediate. Failure is a combination of elastic buckling and localized material failure. Most columns are going to be intermediate, and they're going to be designed using some empirical formulas that are developed through lab testing. We're going to talk about different methods of that towards the end of this chapter. A little bit more about buckling. This guy here, Swiss mathematician Leonhard Euler, lived back in the 1700s, derived an equation to predict what load would buckle a column. Euler presented his formula in 1744, and we're still using it today. It was a very good formula. So let's talk about ideal columns. An ideal column has a pin joint at both ends, so therefore it can be free to rotate about the end point, and then that's really what causes the buckling. And we'll talk about different end conditions. Like in this case, it's shown being fixed, but your typical ideal column has a pin joint at both ends. The slender column will bend under the axial load to a deflection shown. Increasing the load will cause further deflection, and if you go far enough, that deflection will cause failure again below the yield strength of the material. Critical load. That is the greatest load a column can support. It's also known as Euler's buckling load, and Euler formula accurately predicts buckling failures. Here's equation 18.1 for the critical load. We don't usually use equation 18.1 for the critical load. We usually use 18.2, and I'll describe that here in a minute. 18.2 talks about the critical stress. Okay, this Fe is the critical stress, and that's pi squared E divided by L over R squared. L over R is a term we're going to be talking about the rest of this unit, and it's called the slenderness ratio, L over R. You multiply the critical stress, this critical stress, by the area to compute the critical load. That's why I'm saying we don't use equation 18.1. Let's use equation 18.2 and then follow this step here. Once we know the area of the column, then we can use that to find the critical load. Note that in this equation, the only material property is E. That's the stiffness of the part. That's the modulus of elasticity. Material failure, like yield strength, for example, is not in this equation for critical stress due to buckling. We're going to talk about example 18.1 in the examples. Next, here is Euler's equation. Okay, so what we did is we put in the 30 million psi for the modulus of elasticity of steel, and we plotted the critical stress versus the slenderness ratio. And as you can see, here's the curve that we got. So we notice as the slenderness ratio goes way up, our critical stress goes way down. The columns are more likely to buckle at the higher slenderness ratios. Okay, so Euler's formula assumes. Okay, let me pick this up in the next movie. I'm going to start right here. Thank you.